Okay, the last lesson of the chapter is titled 5-7, Roots and Zeros. Both words you've seen before, okay? Roots come from what? No, come on. What's a root? Okay, let's start with the other one. What's a zero? It's where your graph crosses the x-axis. All right. A root is when you solve the equation. Okay. Remember what I said about them? They're essentially what? They are essentially the same thing. Okay. They're essentially the same thing. So the lesson starts basically with me taking everything we've talked about this chapter and tying it all together. Okay, we're going to put a big pretty bow around this chapter. We're going to talk about one new concept, and then we're going to talk about one old concept and expand on it. All right? So the pretty bow is this slide here. All right? Listen to me talk, and then you can decide what you need to write. Okay? You really don't need to write a whole lot because you should know pretty much most of this stuff if you've been paying attention all the chapter. Okay? I'm going to skip the words. I'm going to go down to the example because I think that makes it make sense. Okay? So the polynomial function they want to put a pretty bow around with the chapter is this. X to the fourth plus 2x cubed minus 7x squared minus 8x plus 12. The graph of that polynomial is pictured right here. Okay? It's an even, positive degree polynomial. Everybody see that? Okay? How many zeros does that guy have? 4. Okay? That guy has 4 zeros. All right? Those 4 zeros are where it crosses. They are -3, -2, 1, and 2. Right here. -3, -2, 1, and 2. Everybody good? Okay? Notice the form that's talking about. Okay? P of x, that means function form. Okay? Function form. Zeros, roots, same thing, except now you're talking about it in equations. So not equals 0, but same numbers. -3, -2, 1, and 2. Everybody still good? Okay? Zeros, roots, same things. Put them in coordinates. Still the same thing, except you have your y value, which all of them, since they cross the x-axis, all the y's are going to be 0. Okay, cool. Everybody good so far? The connection to make is this. Your zeros and your roots come from the factors of the polynomial. Okay? For example, let's assume that x to the fourth plus 2x cubed minus 7x squared minus 8x plus 12 does factor this way. X plus 3, x plus 2, x minus 1, x minus 2. Okay? If you remember from when we were doing quadratic equations, that would all equal what? 0. It would all equal 0. After we made it equal 0, we would then do what with all of the binomials? We would, we would solve. Before we solve, we would split them up though, right? We would make it x plus 3 equals 0, x plus 2 equals 0, x minus 1 equals 0, x minus 2 equals 0. Okay? What's x plus 3 equals 0? Solve that. What's that?
3.
What's x plus 2 equals 0 solved? What's x minus 1? Oh, wrong one. Lost track where I was. And then x minus 2. See my point here? Okay? This is a big type. Like I said, we're going to use this a little later on. Okay? And if you remember, there's a specific type of problem from chapter 4 where I gave you the zeros of a quadratic and you wrote an equation. Same concept here. It's the exact same thing, except a quadratic had 2. This can have 3, 4, 5, however many I want it to have. Okay? But your zeros come from solving your factors, just like they always have. There's just more of them now. Algebra. Another talking point, don't really need to write it. Okay? The fundamental theorem of algebra says this. Every polynomial equation with degree greater than 0 has at least one answer, one root, in the set of complex numbers. So of all the numbers in the world, real, imaginary, complex, every polynomial you can solve for it. It has an answer. Not earth-shattering, right? Okay, we've been doing that. You've been doing that for a long time now. What's interesting is the next box. It's the corollary to it. It's the expansion of it. A polynomial equation with an n degree has exactly n roots. Okay? So a third degree polynomial has 3 roots, 3 answers. A fourth degree polynomial has 4. A fifth degree has 5. Okay? Degree is the number of roots you have also. Degree is an important number throughout. Alrighty? Make sense? Okay? Everybody good on that one? Okay. That kind of ends those two things, tying up together. Okay? Everybody okay? Okay, what we're going to do next, we're going to talk about very briefly, okay? What a good looking man. Okay, that is Rene Descartes. Alright, and this is what he came up with. It's called Descartes' Rules of Signs. Alright, don't write the words, it'll just confuse you, to be honest. What Descartes' Rules of Signs teaches us and what it talks about is this. If you go through a polynomial and you count up the sign changes, you can determine the possible number of positive roots that polynomial has. Okay? On the other side of things, if you go through and change all the odd-powered signs of that polynomial, change their signs, and then count up the sign changes again, you can figure out the amount of negative roots a polynomial has. Possibly. Okay? Okay, so we're going to work on this. State the possible, keyword there is possible. It really is. State the possible number of positive, negative, and imaginary zeros of x to the 6th plus 3x to the 5th minus 4x to the 4th minus 6x cubed plus x squared minus 8x plus 5. There, that's a fit. Okay, possible positive, possible negative, possible imaginary. All right, now, the first thing I always do with this is this. I look at my degree. Okay, my degree is what? 6. Okay, my degree is 6. I do that first just so I know it, just so I remember, okay? Because it will come back to play here in just a little bit, all right? First thing you do, you go through the polynomial as it's written. You don't put in zeros. You do it as it's written, and you go from term to term. Okay, assuming it's in standard form, most of them I give you will be in standard form. They should at least. You count up the sign changes. All right. So watch my arrow. We go from x to the 6th to 3x to the 5th. Did our sign change? No. Went from positive to positive. 3x to the 5th to negative 4x to the 4th. Did our sign change? Yes. So I'm going to draw a little loop underneath it right there. Okay, so that way when I go back to count them up, I know it changed right there. Everybody see that? Okay, keep going that same way. Negative 4x to the 4th to negative 6x cubed. Did that change? No. Don't care. Negative 6x cubed to x squared. Did it change? Yes. Arrow there. X squared to negative x to the negative 8x. Yep. Negative 8x to positive 5. Yes. Okay. So, you count those up. How many loops did I draw? 4. You put that number underneath your possible positive zeros. Okay? Remember that the key word to all of this is possible, because it's not definite. All right? It's possible. Now, remember what I said earlier with that last slide? I said make sure you remember this part, the less by even number. Remember that? So, you don't just have possibly 4 positives. You could have 2. You could have none. We don't know. That's why the word possible is here. We don't know what kinds of zeros this guy has. We're just figuring out the possibilities. Okay? Rainey? So that's for your positives. Now, for your negatives, you go through and you switch the sign ahead of each odd exponent. So x to the 6th minus 3x to the 5th minus 4x to the 4th plus 6x cubed plus x squared plus 8x plus 5. That's how you figure out your negatives. On the odd exponents. So 5, 3, and 1. On the odd exponents, you change your sign. So 3x to the 5th made it negative. Negative 6x cubed made positive. Negative 8x made positive. Now, go through that one. I wrote it in red because negative is always red. And do the same thing you did up top. So you go sign to sign. So positive x to the 6th to negative 3x to the 5th. Sign changed. Okay? From there, you go from negative to a negative, from negative to a positive. So a sign change. Rest is positives throughout. See that? Okay? So for your negatives, you have how many? Or 2 or 0. Okay? Those two shouldn't be bad. Okay? Yes. Now, remember what the key word to the problem is? It's possible. These are possible outcomes. That's how, assuming those are possible, that's how you still figure out your imaginaries. So now you go through case by case. What's our degree? 6. Okay? Degree is 6. And what we just learned, this polynomial has to have 6 roots. Okay? Or 6 zeros. Positive, negative, or imaginary. Some combination of 6. So now you go through your ifs. If it has 4 and if it has 2, how many imaginaries does it have? 0. Because you want to make your total be what? 6. So I'll ask you again. Say again. If it has 4 and 2, how many imaginaries does it have? 0. Because 4 plus 2 is 6. Okay? Right. So if it has 2, let's go this way. If it has 4 positives and no negatives, how many imaginaries? 2. Okay? Because 4 plus 0 plus 2 makes 6. All right? Now let's go to 2. If it has 2 positives and 2 negatives, how many imaginaries? 2. We already have it. You don't have to write it again. If we have 2 positive and no negatives, how many imaginaries? 4. 2 positive, no negatives. So right now we're sitting on how many zeros?
So you have to equal 6.
Yes. From what we learned just a little bit ago. Okay? So you go through case by case to make it equal 6. So 2 and 0 and 4. 0, 0, imaginary would be 6. And then you're done. Okay? Now, if you notice something about, it didn't really work with the last example, okay? Every time you have imaginaries, when you do your roots, they will happen in pairs. Okay? They will happen in pairs. Because where do imaginaries come from? Anybody remember? How do we get imaginaries? What do we take to get an imaginary number? Nope.
I?
That isn't imaginary. How do we get there? Square root. You take a square root of something that's negative, and when you take a square root, you put in what? I? No. When you take a square root, you put in plus or minus. You put in the I because it's negative. Okay? So whenever you come up with an imaginary, it's because you have a pair of them. Okay? What the complex conjugate theorem says is just that. What it says is if one root is imaginary, if the positive root's imaginary, then the opposite of it is imaginary. For example, if a and b are real numbers, if a plus bi is a zero of a polynomial, then a minus bi has to be a zero along with it. Okay? It's not optional. It is. Okay? So down here, if 3 plus 4i is a 0 of that polynomial, then 3 minus 4i must be a 0 of the function. Okay? Chamberlain, get a hold of it or I'm pitching it. Make sense? Okay, so for that, we're going to go into this. Okay? This is what should look familiar to you, but we're going to expand it to polynomials. We're going to expand it with imaginaries. Alright? Write a polynomial function of least degree with integral coefficients, the zeros of which include -1, 4, and -2. You did this in chapter 4. Except we had how many zeros each time? Anybody remember? 2. Now you could have 3, you could have 4, could have 5. Won't go bigger than 5. Alright, so those steps were this. You set each 0 equal to x. Okay. You turn that 0 into a factor. So you solve it the other way. So for this one, you're going to do what? Make it x plus 1. I'm going to skip that step, okay? Make it x plus 1 times x minus 4 times x plus 2. You move all 3 zeros to the other side, change their signs, turn them into factors. Alrighty? Now what? Foil. Okay? Foil something. Alright? X plus 1 and x minus 4, x minus 4 and x plus 2. X plus 1 and x plus 2, if you really want to, doesn't matter. You foil something. Okay? I always work it like this, to be honest. I always leave the first binomial alone, and I foil the second too. Okay? Now this is the point where your foiling should be pretty good by now. Okay? So x times x gives you x squared. Your outsides, x times 2 gives you 2x. Negative 4 times x gives you negative 4. Negative 4 plus 2 gives you what? Negative 2x. So I'm skipping writing it out twice. I'm doing that FOIL and combining like terms in my head now. You should be there. That's not hard. Okay? Because it's going to save you a step of writing too. All right? Your last FOIL, negative 4 times 2 gives you what? Negative 8. Once you get it down to here, this should look familiar to you because we started the chapter with these. Okay, so you should know how to do this. So x times x squared minus 2x plus 8, 1 times x squared minus 2x plus 8. Okay, now, here's where you're kind of hoping, I'm hoping you guys have gotten better at this too. because I'm trying to not write as much. I'm lazy. Hopefully you understand the concept. You're going to take this x into all three of these. You're going to take this 1 into all three of these. I'm just going to do it and not write it out twice. Okay? So here's what I'm going to do. Bless you. What's x times x squared? X cubed. Okay, and I'm going to do my x again. So x times my next term. So negative 2x. So negative 2x squared. X times negative 8. Negative 8x. 1 times x squared.
X squared.
Plus x squared. 1 times negative 2. And then 1 times negative 8 gives you negative 8. I'm not saying you have to do that within your head. I'm not saying you have to FOIL in your head. What I'm saying is this. If you don't, from here to here you're missing a step. From this one to this one. From here to here you have 2 steps. You have 2 more lines to write than anybody else. And to be juniors in high school, in Chapter 5 of Algebra 2, I think you should be able to FOIL without having to write it out and combine like terms in the middle. At this point. Okay? What's your last step here? We got to clean this guy up. Combine like terms. So x cubed. Negative 2x squared plus x squared gives you negative x squared. Negative 8x minus 2x minus 8. Now, this example did not use the complex conjugate theorem. Okay, notice how all 3 zeros were positive numbers, or real numbers. Okay, everybody see that? This one, not so much. Okay. This one, write a polynomial function of least degree with integral coefficients, the zeros of which include 2 and 4i. Okay, so first thing, like last time, x equals 2, x equals 4i. Now, if that's all you put, and you try FOILing that, good luck. You're going to have ix terms all over the places. That's why the complex conjugate theorem exists. Okay? Because if 4i is a 0, what else has to be a 0? 4i is the 0, so what else? 4i is the 0. So, no. Negative 4 what? Negative 4i. So, you make sure if you see one that's I, you add the negative one. Or if I give you the negative one, you give me the positive one. Either way. Okay? Your next step, still the same. Move them to the other side. So x minus 2. X minus 4i. X plus 4i. Okay. The reason why on the last one I left this binomial alone first is because of this. Okay. If you are feeling adventurous and want to live dangerously, go ahead and FOIL x minus 2 and x minus 4i. I don't recommend it. I said if you want to live dangerously. What you should do is FOIL which two? The x minus 4i, the x plus 4i. Okay? Because after you FOIL that, since those two are conjugates, keyword from last chapter, what's going to happen to the I? It's going to get squared and changed to negative 1 in the last term, and in the middle 2 terms they what? They cancel. So your first multiplication should probably be your 2 imaginary terms, or your 2 imaginary binomials, okay? So x times x gives you x squared. All right, follow along. 4ix minus 4ix gives you... See, that's what I'm saying. If you do it with the x's and the i's, it gets an nasty. 4ix minus 4ix. 0. Okay? If you do those two, you have IX terms all over the place. All right?
Don't you get negative 1 from this I squared?
Not yet. We're not there yet. So do your last FOILs now. Negative times positive gives you negative. 4 times 4 gives you 16 I times I. I squared. Okay, Ron.
Can you just combine it now?
Yes, if you go straight to positive 16 there, that's fine. Okay, but I'm going to show it on this one. All right. I squared is negative 1. Negative 1 times negative 16 gives you 16. So I have x minus 2 and x plus 16. X squared plus 16. There we go. The nice part about these is if you only have 3, you should end with a FOIL and not a trinomial times a binomial. Okay, so there is a silver lining a little bit. I'm going to reverse FOIL it just so it's in nice order. So x squared times x, x cubed, x squared times negative 2, negative 2x squared. 16 times x gives you 16x. You're a step ahead. 16 times negative 2, negative 32. And there's your polynomial. This one's a much clearer example as to why the i's happen. Okay, remember, if you would solve this, set it equal to 0. Factor out an x squared, you get an x minus 2. Factor out that 8. It'd be that x squared plus 8 that you factor out and left with. That's what gives you your i's. Okay, or it'd be a 16, but you get my point.